A pipe measuring 100 to 200 feet in length is buried at a depth of 10 feet underground. The pipe has a diameter of approximately 6 to 10 inches. One end of the pipe draws in fresh outdoor air, while the other end opens inside the house. A small fan is installed in the middle to push the outside air through the pipe. That's all there is to it. Now here's what happens. During the summer, when the scorching 45 degrees Celsius outside air passes through these underground pipes, the surrounding soil, which remains at a stable temperature of 15 to 18 degrees Celsius, gradually absorbs the heat from the air. By the time the air reaches the other end of the pipe and enters your room, its temperature has dropped to around 25 to 28 degrees Celsius. This happens without any compressor, without any chemical refrigerant gas, and without heavy electricity consumption. And it's not just useful in summer. During winter, when the outside temperature drops below freezing, these pipes are still surrounded by soil that remains at 15 to 18 degrees Celsius. As the cold air travels through the pipe, the warmth stored in the earth gradually heats it up. In other words, this system works as a cooler in summer and as a heater in winter, all through the same structure. Now, if you're thinking, this sounds great, but how can it actually work? Then wait a moment. Let me show you a few numbers that will open your eyes. A typical split air conditioner has a coefficient of performance, COP, of around 2.5 to 3. That means for every unit of electricity it consumes, it provides 2.5 to 3 units of cooling. However, a well-designed earth-air tunnel can achieve a COP of 10 to 12. In other words, with the same 1 unit of electricity, you can get 10 to 12 times more cooling. And how is that possible? A conventional air conditioner requires around 1.5 to 2 kilowatts of electricity to run its compressor and refrigerant system. In contrast, an earth-air tunnel only needs electricity to operate a small fan that consumes just 200 to 300 watts. Where a conventional air conditioner may add 3,000 Indian rupees to 5,000 Indian rupees to your monthly electricity bill, this system can operate for just 200 Indian rupees to 300 Indian rupees per month. But this isn't just a theory. This technology is already working in the real world. In Edmonton, Canada, a 28-story building called Epic Tower has reduced its energy consumption by as much as 60% using this technology. In Harare, Zimbabwe, a building called Eastgate Center, inspired by the design of termite mounds and using earth cooling techniques, remains comfortably cool without relying on conventional air conditioning. And in India, in desert regions such as Rajasthan, this technology is being used to keep large buildings cool while consuming significantly less energy. In desert regions, such as those in Rajasthan, India, this technology is being used to keep large buildings cool while consuming 75% less energy. So far, everything sounds impressive. But if I only talked about the advantages, that wouldn't be honest, because this technology also has some serious challenges that can be dangerous if ignored. The first challenge is moisture and fungus. When hot 45 degrees Celsius air comes into contact with the cool underground pipe, the moisture present in the air condenses into water. It's exactly like the water droplets that form on the outside of a cold bottle. If the pipe is not installed with the proper slope, this water continues to collect inside. Within a few weeks, fungus and mold begin to grow. In 2005, a house in Belgium experienced exactly this problem. The pipe had no proper slope, water kept accumulating, fungus spread throughout the system, and eventually the entire house became unfit to live in. However, the solution is very simple. Provide the pipe with at least a 2% slope and install a drainage point at the lowest end so that the accumulated water can drain out automatically. The second challenge is even more serious, and that is radon gas. In some regions, the ground naturally contains a radioactive gas called radon. If there is a crack in the pipe or if any joint is weak, this gas can enter the pipe and flow directly into your home. Radon is both odorless and colorless. You won't even know it's there, and prolonged exposure can even lead to lung cancer. But there is a solution for this as well. Use high-quality HDPE pipes, which have an almost zero chance of leakage, and have a radon test conducted once every 2 to 3 years. Now, At this point, a very important question arises. If this technology is so remarkable, so affordable, and so durable, then why isn't it being used in every home? And this is where the most interesting part of the story begins. You see, the global HVAC, heating, ventilation, and air conditioning industry is a multi-billion-dollar business. In India alone, the air conditioning market is worth thousands of crores of rupees. The air conditioning market is worth more than 30,000 Indian rupees crore, and the entire business model of these companies is built around one thing. You get your air conditioner serviced every year. Every 3 to 4 years, you have the refrigerant gas refilled. And after 10 to 12 years, you replace the entire machine. This cycle continues, and the companies continue making money. But an earth-air tunnel completely disrupts this cycle. Once it is designed and installed correctly, it can last for 50 to 100 years. There is no compressor to replace, no refrigerant gas to refill, no annual servicing, and virtually no mechanical breakdowns. In other words, from the company's perspective, it is not a profitable business. That is why you will never see advertisements for it on television. That is also why governments have not introduced any clear subsidy or incentive policies specifically for this technology. And that